Let's look at the elevator problem, which is what we have time for. The first thing you have to know is what a scale measures. This is a big hint into this question. Hopefully you know what a scale is. It's what you use to measure your weight, which is what we have down here. This is the thing you step on when you go to the doctors, and it's supposed to tell you your weight. In actuality, scales doesn't exactly measure your weight. It measures how hard you press on the scale. And this is just a technicality, but you'll see that it is important. If we have this block here and it's on the scale, it will measure its weight if there's nothing special going on. But think about when you're at the airport and you're trying to weigh your luggage if you're trying to check it. What happens if you push down on your luggage? The weight on the scale goes up, right? So it's not just about how heavy your luggage is, it's about how hard everything is pushing down on the scale. And you'll see that this actually matters. What it actually measures, if I say how hard you press on the scale, is the normal force between something and the scale. So remember, if we have a block on a scale when it's trying to measure its weight, the scale will push up on this block. And this is why it can stay on the scale. It's going to balance out the weight. When the scale pushes up on the block is also pushing down. Remember what law this is? This is Newton's third law. And this is what the scale measures. It measures the normal force by the object on it. So not just the weight. It just happens to be that the weight is equal to the normal force in most cases. And this is the idea behind a scale. It's that when you stand on it, I'll measure the normal force, and the normal force will be equal to the weight. The problem here is your weight is not always equal to the normal force you put. And let's look at a situation where this happens. The elevator problem. If a person stands on a scale just on their own, just in a normal place, they stand on the scale at their doctor's and it tells them that they weigh 500 newtons. What happens if this same person is on the same scale and they go into an elevator and this elevator starts going up, just trying to go to a top floor? What does this scale read? You have three options here. Do you think it's going to read more than what it said before, 500 newtons? Do you think it's going to weigh the exact same thing? Or do you think it's going to weigh less than 500 newtons? Be careful and think about it. This is an interesting question. And we'll look at two solutions, or two ways of thinking about it afterwards. What you might want to think about is your own personal experience on elevators. What do you feel between your feet and the ground of the elevator when it's going up? You might get it right, you might get it wrong. But the important thing is you try to figure out what it is. You can guess. It might just be, a lot of times it's just a gut feeling. That's a lot of times what physics is about, just a gut feeling, because it's based off of what you know in your real life. We're going to go through the way you get through it, and then you'll see what the answer is. There's two ways to do it that I'm thinking of. There's one way where you think about your effective gravity, or actually this is your effective weight. Some people call it your apparent weight. Next thing, and this has to do with the feeling of weightlessness. And another way is to look at it a bit more mathy. We're looking at Newton's second law, and we can directly use this to mathematically solve for the answer. Let's start with the math way. Let's use Newton's second law to write the solution to this question. We want to first start by drawing a diagram of everything that's happening. Let's first draw a free body diagram. Hopefully you remember what that means. And what should we draw the free body diagram of? We should actually draw the free body diagram of two things. We should first draw the free body diagram of the person. I'll put it in green because this guy's wearing a green shirt. This is of the person. And then we'll also draw a free body diagram of the scale. These are two separate objects, which is why we can do this. The person feels a normal force up. Do we know where this is from the scale they're standing on? And they also feel a weight downwards. This is because of gravity from the earth. I'm going to be careful about exactly how long these lines are. The scale feels a normal force down from the person. This is the Newton's third law pair. So these are the exact same, just in opposite directions. And they're also going to feel gravity pulling down on the scale. The scale itself has its own weight, so it's going to pull down here. And actually you'll find that this doesn't really matter. So we see these two diagrams, and then we can actually write a Newton's third law thing. So remember what we're looking at for the scale's measurement? We're looking at this right here. We're looking at how large this amount is, the normal force. And actually, we can ignore this diagram here. I just drew it to show you the Newton's third law, but we can just find how large this red arrow is. And we can do this by writing our Newton's second law. Remember what it is? It's F net equals to ma. And what's m here? M is the mass of the person. This guy has a mass m. I'll write it in a different color. This guy has a mass m. So we can write our net force. Do we remember how to do this? We add the forces together. What we do is we do the normal force minus the weight of the person. And this is equal to the acceleration. the mass times the acceleration. The mass times the acceleration is going this way, it's upwards. So I'm keeping it as positive. Remember what positive and negative signs mean? Positive here means up, and negative means down. So that's why the normal force is positive, it's going up, and the gravitational force is going down, it's negative. Acceleration is up, so that's why it's positive here, and you want to be careful. So now when we want to calculate what normal force is, which is what we're looking for, this is what the scale measures. We can find that normal force is equal to the weight of the person added to the mass times the acceleration. So what's the answer, guys? If we're doing its weight plus something else, that means the scale is reading something that's bigger than 500. It's doing 500 plus something else. And this depends on how much the elevator is accelerated. So the answer is something larger than 500 newtons. Something bigger than 500 newtons. And the way you can think about this is if you're in an elevator and it starts accelerating up, you can feel when the elevator goes up. It's because the floor starts pressing on your shoes. You can feel that when an elevator goes up, if you have a good sense. Let's look at the second math. This one isn't as much math. It's more of thinking. There's an idea of something called apparent weight. So have you ever heard of the term weightlessness? So for example, maybe if you hit a bump in the road or you are going down a hill, you might feel that you're weightless. And this has to do with your feeling of your own weight, how much you're pressing on the ground. Humans can detect essentially how their weight feels. And the way they detect this is how hard they're pressing on the ground. So for example, if you jump off something, don't do this from a high place, you'll feel that you're weightless. And this is because your feet aren't touching anything. You're just falling. And again, the weightless is not depending on your weight. Your weight is the same when you're jumping or when you're not jumping, but it depends on how hard the floor is pressing on you. So when you accelerate up in an elevator, you actually feel that you're more heavy. You feel as though everything is pressing on you, as if the Earth suddenly increased its gravity. Think about this. If you were on Jupiter, it might feel something like going up in an elevator that's going really fast. It's maybe the same feeling, except that elevator would have to be going really fast. But if you're on the moon, it might actually feel like an elevator that's going downwards, where you feel more weightless. Maybe this makes a bit of sense. So depending on if the way you're accelerating, you'll feel that you're a different weight. If you're on Jupiter, you'll feel that you're a different weight than if you're on the moon. And we can simulate. So this is the moon, this is Jupiter. And you can simulate this by going in an elevator. If the elevator is accelerating up, you'll feel more heavy. You'll feel like you're on Jupiter. And if you're going downwards, accelerating downwards, you might feel like you're on the moon. And this is actually how maybe you've seen a zero-G plane, where people go on a plane and they start floating around and all that cool stuff. Does anybody know how a plane does that? How they reach zero-G? So what a zero-G plane does is it goes in this path. So the plane first, this is our plane, it's just a block. It flies up and it has all the thrusters on, the wings are doing its thing. And then at some point, they turn off the engines. They'll just turn off the engines and they can't turn off the wings, but their goal is to make it feel as though you're just falling. So in this point, this part that's called zero-G, it's not actually that you're in zero-G, it's that you're free falling. Your acceleration is equal to G. When you're at other parts of a plane, the plane's pushing up on you. But when you're in zero-G, you don't touch the floor anymore. The plane is falling with you and you're also falling with the plane. So zero-G is actually when the plane is falling. It's going in this part and there's no engines on, and the goal is to make you feel like you're just falling. And this should be the same feeling as if you're falling off of something. If you're falling off of something, you're as though you're in zero-G. Maybe if you're in a falling elevator, for example, the cables snap and the elevator starts falling, you're going to be in zero-G. So that's something interesting. And this is a direct application of this.